All right. So we are going to skip over chapter 3 right now, and we're going to move into chapter 4. Chapters 4 and 5 deal with some trigonometry stuff that is important for you guys to know. So this is what we're going to do. Today what we're going to do is look at what is radian and degree measure. Most of you should be very familiar with degree measure. You may not be as familiar with radian measure. Let's see. So here are the things we are going to do is we're going to talk about some angles in probably a little bit different way than you're used to. We're going to use radian measure. We're going to convert between degree and radian measure. And then we're going to look at some real life type problems. All right, so angles. All right. Just a little background on trigonometry here. It says from the Greek language, the word trigonometry means measurement of triangles. And all of y'all have done trigonometry stuff where you've done sine, cosine, tangent, SOHCAHTOA, opposite over adjacent, and we'll get to some of that stuff. But there's a much more broad thing that trigonometry deals with. Initially, trigonometry dealt with relationships among the sides and angles of triangles and was used in the development of astronomy, navigation, and surveying. And then with the development of calculus and the physical sciences in the 17th century, a different perspective arose, one that viewed the classic trigonometric relationships as functions with the set of real numbers as their domain. So it just sort of expands upon, and if you are going to go into calculus, this is the type of stuff that is going to help you quite a bit. Some applications of trigonometry expanded to include a vast number of physical phenomena involving rotations, vibrations, sound waves, light rays, planetary orbits, vibrating strings, pendulums, orbits of atomic particles. So a lot of things that are out there in the real world have trigonometry in them. So that's why it's very important that we cover it and all that. So we're going to talk about angles first. Okay, and we all have we've done angles. You've measured angles maybe with a protractor. You've talked about acute angles, right angles, straight angles, obtuse angles, and all that. And that's all going to apply here, but we're going to look at some things a little bit that you may not have seen before. An angle is determined by rotating a ray or a half line about its endpoint. The starting position of the ray is the initial side of the angle, and the position after the rotation is the terminal side. So this is one thing that you probably haven't dealt with a whole lot when you're dealing with angles, is one side being the initial side and one side being the terminal side. And as the terminal side moves away from the initial side, that's the angle that is created. Notice the vertex is still the corner of it. But when you're dealing with trigonometry, we do sort of look at this angle as there's an initial side where it starts, and then you can open the angle up, or you can even open it down to create different angles. And if you'll notice, generally in trigonometry, what we do is we set up a coordinate axis, right? And the initial side, the vertex is put at 0, 0. And then the initial side is going to run out here along the x-axis. And then we can open the angle up, and then you have this angle created right here. But as you'll see also that you could also open the angles up underneath, and you could have angles down this way. Okay, and we'll talk about that. As you can read through here, the endpoint of the ray is the vertex of the angle. This perception of an angle fits a coordinate system in which the origin is the vertex and the initial side coincides with the positive x-axis. Such an angle is in standard position as shown in figure 4.2. So this is what we consider standard position of an angle. So like I said before, we can either open up or we can open down. Notice that when you open up and you go from the initial side towards the terminal side in a counterclockwise motion, this is a positive angle. You're going to get a positive result. Okay. Now, if we open and take the terminal side down and we're looking at this angle that's created down, this is where we can get a negative angle. Okay. So be aware of that. When we're talking about negative angles, they are talking about the angle that is created by going from the initial side and going clockwise from there. All right. The positive angles are counterclockwise from the initial side. All right. A lot of times you'll see these Greek letters used to label angles. They've got the Greek letter alpha and beta. You also see theta quite a bit. As well as, and what you've used probably most of your time in math is just regular letters A, B, and C, capital A, B, and C to recognize angles. You know, we've in the past you've had to use 3 points to name an angle with the vertex in the middle. If it was the only angle, you could use just a vertex. But in trigonometry, a lot of times we're going to use these sort of Greek letters. And theta is the one we're going to use most. And theta is going to look like, theta is a circle with a line through it. This is theta. This is just a Greek letter. It's a variable like any other letter, X, Y, or Z, or whatever. But it just helps when you see that, you know they're talking about an angle. Note that angles A in this case and B, notice that these two angles are created by the same ray over here. And what they are, alpha and beta, are considered to be coterminal angles. The measurement of this angle and the measurement of this angle are coterminal because they come from the same actual two rays. Same thing here. Notice how this one is done. Two different angles that use the same ray. We've got this angle here that goes up this way. We could have taken the measurement here, a negative angle. That would be coterminal. But notice what they did. They started here and they went all the way around 360 degrees and then to there. And that's something we're going to talk about, as you can create as many angles as you want by continuing going around. You could go around as many times as you want. It's like if you were standing there, you spinning in a circle. How many degrees would you be spinning around? You spin around once, that's 360. You do 2 spins, that's 720 degrees, and so on. But that's what they're talking about. We'll talk about that more here as we go. All right. Now, like I said, we're very, very familiar with degree measurements. You may not have heard of radian measure, but it's just another way to measure an angle. Okay, and that's what we're going to get into now. All right. The measure of an angle is determined by the amount of rotation from the initial side to the terminal side. One way to measure angles is in radians. Okay, now, like I said, we're used to degrees, right? A 90-degree angle right there. A straight angle is 180 degrees. All right, we could have one that's a little bit smaller, have it 30 degrees and all that. But what we're going to do is another way that's more commonly used in calculus and trigonometry is radian measure. So that's what we're going to talk about here. All right, so let's talk about where they get radian from. Okay, like I said, it's very, very useful in calculus. Now, to define a radian, you can use a central angle of a circle. So what we've got is we've got this circle, and this is something you're going to see in the next couple weeks. Circles around this coordinate axis will get to what's called a unit circle. But to define a radian, you can use a central angle of a circle. So what they mean by central angle is if I drew an angle with the vertex right there in the center, all right, where I've got one side here, goes out to the other side, right? I'm almost cut out like a little pie shape. And here, there's the theta. Here's the central angle that is created right there. Okay. And notice what's being created here is this circle from the vertex to that's the radius, right? From the center of a circle to the edge is the radius. So both of these are the same length because they're going from the center to the edge of the circle. But notice a radian is created when you take the length, the arc length, this little part right here, okay? So if we take the length of the radius, and if we were to sort of stand that up and then be able to bend it over and lay it along the circle, all right, 1 radian, all right, that measurement is 1 radian when the radius length of the circle, of the angle, the length of the angle is the same as this arc length, all right? That's when the degree is 1 radian. So we don't have any numbers here, but we know this would be 1 radian. Okay, and let's expand upon that. All right, so 1 radian is the measure of a central angle theta, right? Just that variable that we're using, the Greek variable, to sort of make it easy to pick out what's the angle that intercepts an arc equal in length to the radius of the circle. So, right, so we've got here and we've got the circle. So you got this radius of the circle, all right, whatever that is. If we were to stand the line up that same length and then curl it over to the circle where that length, so this length, this arc length, and this length are all the same. They're all R. That's what's happening here. That makes this angle 1 radian. So let's read through this again. 1 radian is the measure of a central angle theta that intercepts an arc S equal to the length of the radius of the circle. Algebraically, that means, so what that means is theta, this angle, is going to be the length of the arc length divided by the radius. Okay, so in this case, the arc length, the S, is equal to R. So that is basically, if S is equal to R, what we have is R over R, and that's where we get 1 radian when the arc length is the same as the radius. Now, if the arc length is not the same as the radius, so we have, here's our initial side, say it goes up to here. Now this is still the radius and still this is the radius, but now we have a much longer arc length. Well, the measure of theta in radians will be the length of this arc, which is S, divided by the radius of that circle. All right. Now, if we're going to look at a full, let's say we have, let me try to redraw this. I'm running out of space. We have that circle. Here's our initial side. If we take and go all the way around the circle, 360 degrees, we know that is 360 degrees. If we go all the way around, where basically the initial side and the terminal side are both the same, all right, that the theta there initially becomes the S, which is all the way around divided by radians. And we know the circumference of a circle is 2 pi R. So then for an entire circle, 360 degrees, we can find the arc length by taking 2 pi times the radius. All right, because the circumference is 2 pi R or pi D, but we're going to use radius here. All right, because the circumference of a circle is 2 pi R units, it follows that a central angle of 1 full revolution corresponds to an arc length of 2 pi R. All right, now that doesn't make a lot of sense to you. We're going to use that as we move forward. All right, moreover, because 2 pi, if we were to put what? 2 times the estimation of 3.14. That equals 6.28. All right. What that means is in a full circle, there is just over 6 radius lengths in a first full circle, right? Here's one radius. If I kept adding them, 2, 3, 4, 5, 6, and then just a little bit more. All right. There are just over 6 radius lengths in a full circle, as shown in this figure. Because of the units of measure for and are the same, the ratio S over R has no units. It's simply a real number. We don't have to name like degrees. We call it 50 degrees or whatever. With radians, it doesn't have a unit because when you take the arc length, say you were measuring that in inches, the radius is in inches. When you divide inches over inches, the inches cancel and we're just left with the number that's left, simply a real number. All right. Now let's move on and get to all right. So go back to this you've had a long time ago. If we look at just the coordinate axis system, right, it gets divided into 4 quadrants. Quadrant 1, Quadrant 2, Quadrant 3, and Quadrant 4. This becomes important now in this part of trigonometry because of these angles, because a lot of times we look at what quadrant does this angle end up in, okay? Notice any angle that finishes it when you go from the initial side here to here, this terminal side is in Quadrant 1, all right? Now, we said going all the way around the circle is 2 pi, right? Because we said, if you go back to the previous, all right, the radius of that circle, if the radius is well, we'll call it 1, 2 times 1 times pi gives us the circumference of that, okay? So if one circle is 2 pi, all right, half of that's going to be pi. A quarter of that would be pi over 2, right? If I divide pi over 2. So that's how they get the separations. Anything in Quadrant 1 goes from a radian degree of 0 to pi over 2. Quadrant 2 goes from pi over 2 to pi. Quadrant 3 is pi to 3 pi over 2. And 3 pi over 2 to 2 pi is where Quadrant 4 is. All right. Notice angles in Quadrant 1 are acute. Angles in Quadrant 2 are obtuse. Of course, if you looked at going the other direction, negative angles down into those quadrants, it would work the same way. All right. Now, we talked about coterminal angles is basically when we have this angle here and possibly going around the other way, 2 angles that have the same terminal side. All right. They are called coterminal, right? They share a terminal side. All right. So for instance, the angles 0 and 2 pi are coterminal. Well, what would be 0? 0 would be an angle where both rays are sitting right on top of each other, right? And then if I went all the way around to 2 pi, all right, and I look at this angle that goes all the way around, notice the angle 0 and angle 2 pi share a terminal side. All right. Now, I could continue to find an infinite number of coterminal angles because I could keep going around, like we said a minute ago, 360 degrees, 720 degrees, so on and so forth. So if a full circle is 2 pi, 360 degrees is equivalent to 2 pi when you're talking about radians, right? Okay. Every time I add 2 pi, I go around and I can come up with another coterminal angle. That's what this is saying right here. The number of times I add 2 pi, all right? Now, what they're saying is pi over 6, which is, this is pi over 2, pi over 6 is going to be somewhere right over here. To find coterminal angles, I've got that angle. I could go all the way around. to find that angle. I could go all the way around. I could keep adding 2 pi to pi over 6. Also, if I wanted to go the other direction, instead of adding 2 pi, I could subtract 2 pi to find an angle that is coterminal with pi over 6. All right. So here's what they're doing there. All right. So for the positive angle, theta equals 13 pi over 6. All right. Subtract 2 pi to obtain a coterminal. So they're just wanting to know, what's a coterminal angle for 13 pi over 6? All right. Whatever angle that is. All right. Well, I could add 2 pi or I could subtract 2 pi. Either way, it's going to leave me with a coterminal angle. So what they did is they subtracted 2 pi. And so if you have a fractional calculator, you could say 13 over 6 minus 2 over 1. If you're going to do it by hand, you would have to find common denominator, right? Which the denominator would be 6. So this would be minus 12 pi over 6. And 13 minus 12 is 1 pi, which would just be pi over 6. So there is a coterminal angle, and pi over 6 is that one right there. So this one is the 13 pi over 6. This one is pi over 6, and those are coterminal. I could find another coterminal by subtracting another pi over 6. If I wanted to, that would then tell me this angle here. All right. All right, for the positive angle, 3 pi over 4, subtract 2 pi to obtain a coterminal angle. So now here's just showing you can also subtract 2 pi. All right, so to find coterminal angles, you either add 2 pi, you add 360 degrees, or you subtract 360 degrees, whichever way you want. In this case, they're subtracting. All right, so here is 3 pi over 4. That's this angle. So now they're wanting to subtract 2 pi to find what this angle is. So same thing, you can use a calculator if you want, but common denominator of 4 would make that 8 pi over 4. And then 3 minus 8 is negative 5 pi over 4. Negative angle tells me that I'm going clockwise from the term or from the initial side. And there we have. I could keep subtracting 2 pi to find more and more coterminal angles, or I could have taken 3 pi over 4 and added 2 pi and kept adding 2 pi to find coterminal angles. And that's what they did here. The negative angle of 2 pi over 3. All right. Remember, right here, 180 degrees is equal to pi. So negative 2 pi over 3 is going to be right here. Is where they're going with it. All right. And so they want, that's a negative angle, and they want to, they're asking you to this time, we could subtract 2 pi. That would go all the way around. That would find that coterminal angle. They're saying to add 2 pi so that we can find the measurement of this angle, which is coterminal with it. And notice when they take negative 2/3 pi and they add 2 pi, which that would be 6 over 3, right? And then negative 2 plus 6 is 4. So I get 4/3 or 4 pi over 3. And that's where they get that measurement right there. So to find coterminal angles, we're just either adding 2 pi or subtracting 2 pi, right? 2 pi, right? We go all the way around a circle. We know that's 360 degrees, which is equal to 2 pi. 180 degrees over here is equal to pi, half of that. Half of that we know is 90 degrees, which half of pi would be pi over 2. Half of 90 would be 45 degrees, which half, if we divide that, would be pi over 4. Okay, and we're going to talk about in just a minute how to actually convert from degrees to radians. We're going to talk a little bit about degree measure here. All right, this is you're much more familiar with. The second way to measure angles in terms of degrees is denoted by the symbol degree, the little degree symbol. A measure of 1 degree is equivalent to a rotation of 1/360, right? Because we know there's 360 degrees in a complete circle or a complete revolution around this coordinate axis. To measure angles, it's convenient to mark degrees on the circumference of a circle as shown. So write degrees. We know we're very familiar with 90-degree angles, so we know half of that, halfway between that, and that's 45. 30 is a little bit less, 60 is a little bit more. These are the major angles that we're going to need to know about in trigonometry. But we know, we've seen this before. You go all the way around to 360. All right. Where they get the 30-degree, well, it's 1/12 of 360. It's no big deal there. All right. So a full, and we talked about this a minute ago, full revolution counterclockwise corresponds to 360 degrees. A half revolution is 180 degrees. A quarter is 90 degrees, and so on. Because 2 pi radians corresponds to 1 complete revolution, degrees and radians are related by the equations. 360 degrees equals 2 pi radians. And also 180 degrees equals pi radians, right? We discussed that. All right, from the second equation, you obtain 1 degree equals pi over 180. So what they had was 180 degrees equals pi radians, right? So if I divide both sides by 180 degrees, that cancels and leaves me 1. One degree equals pi over 180. And if I went the other way, if I had 180 degrees equals pi radians, if I divided both sides by pi, I would have 1 equals 180 degrees over pi. 1 radian equals 180 degrees over pi. 1 degree equals pi over 180. And this is what leads us to how we convert from one to the other. All right, to convert degrees to radians, multiply degrees by pi over 180 degrees. All right, so if I have 90 degrees, to change that to radians, I multiply it by pi over 180 degrees, and notice what I would have is 90 pi over 180, which is 1/2 or pi over 2. To go from radians to degrees, you just multiply it by the inverse, 180 degrees over pi radians. So if I had 3/2 pi as my radian degrees, whoops, let's go back. I would multiply that by 180 degrees over pi. Notice pi's would cancel, and then 2 goes in 193. That's equals 270 degrees. All right. So that's basically how we convert. All right. Degrees to radians, pi over 180, radians to degrees, 180 over pi. Multiply by that. All right, so this is where you need to start recognizing what radians and matches up as degrees. Notice 30 degrees, right, is equivalent to pi over 6, right? We said, so if we have 30 degrees, we want to change that to radians, we would multiply it by pi over 180. And what we have is 30 over 180. 30 over 180 pi, and 30 goes into 86 times, so we end up with 1/6 or pi over 6. That's how we're getting that. 45-degree angle is equivalent to pi over 4. A 60-degree angle is pi over 3. 90 degrees is pi over 2. 180 degrees is pi. And we've already discussed how 2 pi is equal to 360. Okay? So we need to start becoming familiar with these radian degrees. I think we're very familiar with and can visually think about what degrees are, but we need to be able to start comparing them to radians. All right, so here's just a couple examples like we just did. 135 degrees. So I'm going to multiply, if I wanted to go change it to radians, I'm going to multiply it by pi over 180, which ends up being what, 135 over 180 pi. And then if you have a calculator, if you, however you want to reduce your fraction, 135 over 180, most of your calculators will reduce it. That reduces down to 3/4. So this is 3 pi over 4. 135 over 180 is 3/4. So that's radians. And I guess it's going to show you that here. Yep, multiply by pi over 180. All right. 540 degrees is basically 540 over 180. And we're left with a pi. What is that going to equal? Is 3 pi radians. So 540 degrees is equal to 3 pi radians. Negative 270 degrees. All right, so we're going to take negative 270 and put it over 180, which negative 270 over 180 reduces to negative 3/2. So negative 3/2. And then we're going to put the pi there. So negative 3/2 pi. All right, so once you get the hang of it, it's very simple. All right, you've talked about complementary and supplementary angles before in geometry or whatever class you had. Complementary angles mean that they add together to 90 degrees. Supplementary angles are two angles that add together for 180 degrees. The only difference here is we're talking about radians also. So complementary angles add to pi over 2. That's equivalent to 90 degrees. And supplementary angles add to pi. I've always remembered it because alphabetical order and numerical order. So here are two complementary angles, right? They combine to form a 90-degree angle. So these two are going to add to pi over 2 or 90 degrees. And then these two form a straight angle, are going to add to pi, very good, pi, or 180 degrees. All right, so if I want to find the complement and the supplement, all right, so supplements or complements add to 90. So for A, if I want to find the complement, I would just take 90 minus 72, which is what, 18 degrees? For the supplement, I would take 180 minus 72, which is what, 108? All right, for B, 148, or I'm sorry, that's going to be, the complement's going to be 90 minus 148 degrees. And that's going to end up being a negative angle, right? I believe that's right. 90 minus 148 is negative 58. So these two angles are not this one. 148 and negative 58 are complements. The supplement, I would say 180 minus 148, which is what, 32 degrees? All right. For radians, it's the same thing. For C, for the complement, 90 degrees or pi over 2, I'm going to take pi over 2 minus 2 pi over 5 to find the complement. So I'm going to take 1/2. If you have a calculator that handles fractions, this makes it a lot easier. Minus 2/5. And that is 1/10, or pi over 10. And then the supplement is 180 degrees, which is pi minus 2 pi over 5, which that's going to be 3 pi over 5. All right. And let's make sure I'm doing these right. 18,108. There's a supplement, complement of this. That's one we just did. Pi over 2, which is 90 degrees, minus 2 pi over 5, which turns to 5/10 minus 4/10, which is 1/10, or pi over 10. We're going to subtract from pi to get the supplement. So pi minus 2/5, or 1 minus 2/5, right, is 3 pi over 5. And then this one, well, let's back up. There's where I messed up. Supplements and complements cannot be negative angles. So you notice what they said there, because 148 is greater than 90, it has no complement. I forgot to do that. I was just blindly subtracting. So you can't subtract a bigger number from a smaller number to find a complement or supplement. So if the number is greater than 90 degrees, it has no complement. All right, it only has a supplement. If it were over 180 degrees, it wouldn't have a supplement. All right, so that's why there and there. But the last one, because 4/5 is greater than pi over 2, there is no complement. It's bigger than 90 degrees, so there's no complement, but we can subtract it from supplements. So you have to end up, when you're looking for complements and supplement, you're only looking at positive angles. Okay, so sorry, I didn't clarify that earlier. So we end up with pi over 5 there. All right, last thing we're going to talk about is linear and angular speed. And this is sort of all dealing with the same thing. The radian measure formula, theta equals S, right? That was the arc length over the radius. Can be used to measure the arc length along the circle. All right, so for a circle radius r, a central angle, a theta intercepts an arc length S given by S is equal to r theta. So notice what they just did is they just solved this up here for S, which is the arc length, multiplied by theta. All right, so if I want to know the arc length, this is where radians come into play, because it doesn't work with degrees, it only works with radians. If I want to know the arc length of a circle, so if I have a circle, and I've got this arc length right here I'm looking at from here to here. Well, if I know the radius and I know the angle, then I can find what this length is. All right, by taking the radius times the angle measurement in radians. All right. So here it is. A circle has a radius of 4 inches. Right? The radius is 4, so that means this is 4 right here too. Find the length of the arc intercepted by a central angle of 240 degrees as shown in figure 4.15. So this is a 240 degree angle. So what they're wanting to know is what is the measurement of this arc length. And we said it was S, the arc length equals theta times the radius. Well, I can't do it in degrees, so I have to first change 240 degrees to what? Radians. So I've got to multiply by pi over 180 degrees. So 240 over 180 simplifies to 4/3. So this is going to be 4 pi over 3. So this angle, I'm not using degrees, is 4 pi over 3. All right. Now to find that arc length, I just take that measurement, which is 4 pi over 3. And I multiply it by the radius of 4. So if I want to be exact, that's going to be what? 16 pi over 3. And if I wanted to find out about how much is that actual arc length, then I would use 3.14 or the pi button. Let's just use the pi button on our calculator. 16 pi over 3 is about 16.8. So this arc length is 16.8, and radius is inches. This is inches, so this is about 16.8 inches. So just put your angle in radians form, multiply it by the radius, and that will tell you the arc length of that circle. All right? Not real hard. And there they go. They're converting it to radians, and then they're multiplying it by the radius of 4. And notice they get 16 pi over 3, which is about, they said they rounded to 2 decimal places, 16.76. Note that the units for theta are determined by the units for r, because theta is given in a radian measure and therefore has no units. So you have to look to the radius for the units, whether it's inches, feet, yards, whatever. All right, a couple other things that deal with that: linear and angular speed. Consider a particle moving at a constant speed along a circular arc of a radius. If s is the length of the arc traveled in time, then the linear speed is simply the arc length divided by the time, right? Speed is like miles per hour, is just how many miles did you drive and how much time. You take the miles and divide it by the time, the hours. All right, well, to find angular speed or linear speed, right, when we're talking about a circle, and say this is moving around the circle, what's the speed? We simply take how far the arc length was, and we divide it by the time, and that will tell us the linear speed. Angular speed is going to be the speed that the angle is growing or moving. To find that, then you would just simply take the measurement of the angle divided by the amount of time. So linear speed is going to be measuring the arc length and dividing by how long it took it to do that. The angular speed is going to be measuring the angle as it grows and how fast did it grow by taking what the angle ended up being and how much time did it take to grow there. Linear speed measures how fast the particle moves, and angular speed measures how fast the angle changes. All right. So that's just, if you have a basic understanding of how you get how fast is going, this is going to help, right? Miles per hour, how fast you're driving down the road is how many miles you go divided by how much time it takes you to do it. All right, so for an example here, they've got a clock. A second hand of a clock is 10.2 centimeters long. And as shown in this figure, find the linear speed of the tip of this second hand. So they want to know, based on how long this radius is, how fast is the tip of this moving as it ticks its way around the clock? Tick, 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 tick. All right. Well, it doesn't really give us, it does give us the length of the radius, which we said, what was it before? Linear speed is arc length divided by time. So linear speed is going to be the arc length divided by time. And all they've given us is the radius. Well, what do we know about a clock? Well, how long does it take for a minute hand to go all the way around the clock in seconds? It takes 1 minute or 60 seconds, right? And how many degrees, right? Well, what do we need? We need to know the arc length. So what is the arc length all the way around the circle? Well, if we know the radius, this is going around, how far is it traveling? Well, that's just basically the circumference of a circle, right? If it was a unit, if it was 1, we know that would be 2 pi. But because the radius, right, the circumference of a circle is 2 pi times the radius, well, we know 2 pi times 10.2 is going to be the circumference or the distance that the end of that second hand travels, which is what, 20.4 pi. All right. So if we want to know the speed of the tip of that thing, we're just going to take the distance it travels, which is 20.4 pi centimeters, divided by how long does it take to do that? 60 seconds. All right, so then I'm just going to put this in to 20.4 pi, and I'm going to divide that by 60. And that is about 1.07 centimeters per second. So that's the linear speed. At the end of that. So all you really need to know, well, the two things you need to know is how far, or the circumference of the circle, or the distance, could be just an arc length, and how long it takes, which we know is 60 seconds. And let's watch them step through it here. One revolution the arc length traveled is 2 pi r. That's just the circumference, which is equal to the s this time. And there we have 20.4 centimeters. Took 60 seconds. And then we just plug it in and divide it out. And there you go. That sort of covers everything. I'm going to also attach a couple of videos, YouTube videos that help explain through this if you're still having a little bit of trouble. But I'll also activate the assignment, and that's going to be it. I can figure out how to get out of this, and I need to